Mikhail Breslav, and this is work that's done with my advisor Margaret Betke and co-advisor Stan Sklarov at Boston University, and also a biologist, Ty Hedrick from University of North Carolina. So the problem that I'm going to be talking about is landmark localization. And in particular, the domain that we're working with is images of moths. So on the left, you see an image of a moth, and that's our input. And what we want to do is localize automatically 4 key landmarks: the left wingtip, the right wingtip, the head, and the abdomen tip. And we also have a small training set that we're going to leverage. So our training set contains images of moths that also have these 4 landmarks annotated for us. So the question is, what are we trying to do here, and what's the motivation? So one of the motivations for being able to localize these key landmarks of the moth is that if we can accurately do this in multiple views, then we can get a 3D pose by triangulating those landmarks, and now we have a quantitative piece of information about how the moth is moving over time. So in particular, there are 2 communities that care about the 3D pose of moths. First of all, one of them is biologists, because they're looking to understand fundamentals of flight. In particular, with the moth, they stick the moth into a wind tunnel, and they want to know how does the moth respond under varying wind conditions. Also, there's the aerospace community that is interested in essentially building flying vehicles, and they look at inspiration from biology. So now I want to give you a little bit of insight into what drove my method. So again, we're looking at the training set here where we have 4 landmarks annotated for us. And if you think about traditional part-based models, such as pictorial structures and its derivatives and also those based on poselets, they only model parts that have been annotated in your data set. So if a region of your data set is not annotated, those models are not going to capture it. And this is a huge problem when you have data sets with relatively few annotations, because that means large regions of your image are not modeled. In the case of the moth here, for this data set, that means most of the wing and abdomen are not represented by traditional models. So now I'll briefly describe the proposed approach. So what we want to do is we want to be able to automatically discover parts from regions of our training images that have no annotations. And essentially the way that we do this is by generating patches and clustering them. And these clusters of patches, some of them correspond to parts that are going to be useful. Now, when we obtain these clusters of patches, what we also try to do is associate some of those clusters with a landmark if that part is predictive of a given landmark. So let me give you an example. So in this case, the row that's circled with the purple rectangle shows you 5 different parts that are automatically discovered from our training set And these parts in particular are predictive of where the head is. So that means that if we can localize in a test image where these particular parts appear, we can use those to predict the head. So here, what you can see on the test image to the right is we're detecting various parts that are discovered, and those detections are the blue circles, and we're using those other parts to predict where the head is. So the end result is that by using our discovered parts to help predict where the landmarks we care about are, we can get more accurate appearance likelihood terms. And if you go back to those traditional part-based models, you can stick this appearance likelihood term back into a traditional part-based model, and you end up getting a more accurate output. So to talk about the results, essentially, no surprise, we do better than a baseline, which is based on mixture of pictorial structures, and we also outperform a biologist. If you have questions, please see the poster, and if you're hiring, let's talk.